Vectors are quantity that comes with both magnitude and direction. In fact, I think you guys already know some stuff about vectors. In kinematics, you were already exposed to vectors quantity. For example, you first learned about distances. Distance is called a scalar quantity because it just has a magnitude. And then you learn about displacement. Displacement is a vector quantity because we talk about positive and we talk about negative. So on top of just the distance, we add in a direction to this distance, and that together forms for us a vector quantity. Let me give you another example. Let's say we have an origin here, and let's say we have a point P here. And the distance from O to P, this length here is, let's say, 5. So the distance from O to P is 5, but at the same time, if we want to add in a directional quantity to OP, maybe we can take a look at O and we realize that from O, with reference to the North Pole, it is slanted at an angle in a clockwise direction at 45 degrees. So it is not just, OP is not just going to be a distance of 5, but it has a bearing of 45 degrees. So this additional information, when it is added to 5, gives us a direction to OP, and together that forms for us a vector quantity. In fact, a very common and very efficient way to represent vector quantity can be found on a Cartesian axis. Let me show you an example. A Cartesian axis, which is a xy axis. So let's say I have an x-axis here, this is the x-axis, and let's say we have a y-axis here. And I have a point here, let's say I call it P again, okay? So this has a coordinate of 3, 4. And if this is the origin, if I were to connect the origin to here, and I were to talk about a direction from O to P with the distance of OP, this can be represented on a Cartesian axis, and the notation that I'm going to make use of to talk about this vector OP can look something that is like this, OP with an arrow on top. Or if I were to call this vector P with a tutor, it is also representing the same thing, the vector OP. And in books, in our questions, sometimes what they will use to represent P with a tutor is to bold the P. So the moment when you see a bolded P, a bolded alphabet, most likely that represents a vector quantity. And with reference to this, if we were to try to translate this 3, 4 into a vector quantity, we can actually write it in the form of a column vector. So for this particular vector OP with reference to 3, 4, that means starting from the origin, it ends here. This can also be represented in the column vector form as vector 3, 4. And this vector 3, 4, because it starts from the origin, it is fixed to the origin. This vector here is called the position vector. Okay, so the moment when you see this word, you know that this vector starts from the origin. Why is it so special that we need to know that the vector starts from the origin? Because if you were to just look at 3, 4, 3, 4, it can also be representing another kind of vector. I'm going to call it the free vector, which means that as long as it goes 3 to the right, 4 upwards, it is going to be also called 3, 4. It can maybe be here. Let's say this is vector Q, which means that as long as Q has the same direction as P and it has the same magnitude as P, this Q here can also be called 3, 4. So Q is 3, 4, P is also 3, 4. By themselves, we will not be able to tell whether they start from the origin, which means that for a vector to be a position vector, a vector that starts from the origin, we need to be given this definition by the question. But at the same time, if the question had already told us that, hey, this is a position vector, so if P is a position vector and it starts from the origin, that means this point here, the end point, or very commonly called the terminal point, the initial point, the terminal point for this particular vector, because it is a position vector, will bear a coordinate of 3, 4. So they are very closely related. But if it is a free vector, by default, we will just assume all vectors to be free vectors until when the question defines for us that it is supposed to be a position vector. So for a free vector 3, 4, it just simply represents that it goes to the right by 3 from the initial point, and then to the terminal point, going by 3 and then going by 4. So it has less to do with the coordinates of the initial and the terminal point, but for a position vector, yes, the initial point is going to be at 0, 0, and the terminal point is going to be at 3, 4. So we have position vectors. Please take note of this. It is going to be very, very common in H2 math. We have free vectors, and we have this zero vector. Zero vector is weird because although it is a vector, but it has no direction. So what is the use of a zero vector? Let's say we have this vector p, and then we want to add it to another vector, let's say negative p. So what do you think is p plus negative p? We're going to be talking about vectors addition in a short while, okay? But just from your arithmetic, what do you think is p minus p? Is it 0? But if you were to write it as 0, isn't it weird? Because for a vector quantity added to another vector quantity, I should be getting a vector result, not a scalar result. That is why if I have a vector p minus another vector p, which cannot be a scalar result, we will add in a tutor. And this is the zero vector that you are seeing here. Okay, the zero vector or the null vector. And at the same time, there's this thing called equal vectors. Like for example, p and q, they are equal vectors. They're equal vectors when they share the same magnitude and they share the same direction. So this is 3, 4, this is 3, 4. They are equal vectors. If they can share the same magnitude and the same direction, which means that it is also possible for them to share the same magnitude and opposite direction, and that will be negative vectors. So let me draw a free vector that is a negative vector of p, which can probably look something that is, let's say, like this. Okay, hopefully you are seeing it as something that is of the same length. So they share the same magnitude, but I'm going to make it opposite direction. So r is going to be negative of p. They are negative vectors. And we have been talking about magnitude, magnitude, magnitude. So how do we represent magnitude in the form of a notation? So if it is OP as the vector, the magnitude of OP is by making use of the modulus notation. So this will represent the magnitude of OP, like what I've written here in the outline. So magnitude of OP, which is going to be also represented as modulus of P with a tutor, or of course P with a bolded, P that is bolded. And it is also going to be modulus of 3, 4 if P is represented in the form of a column vector. I just want to be a bit more specific because vectors need not always be represented as a column vector, but representing as a column vector is a very, very useful way for us to talk about vectors, to calculate vectors. We're going to see them in examples in a short while. So how do we calculate the magnitude? Extremely easy because it is basically just the length that we are seeing here on the Cartesian axis. And how do we calculate this length? We can just simply make use of the Pythagoras theorem, right? If I were to make use of the Pythagoras theorem, I see a right-angled triangle here, where this distance here is 3, this distance here is 4, which means that in this case, what is the modulus of vector p? What is the magnitude of vector p? It is going to be square root of 3 square plus 4 square, which is square root of 25. So the magnitude is equal to 5. Magnitude is always going to be positive. Okay, regardless of how you are drawing this vector, magnitude is always going to be positive. So in general, if you are given a position vector or if you are given a column vector, then the magnitude of that vector is going to be square root of x squared plus y squared, like what I've indicated here. Okay? And we can also multiply a vector by a scalar. We cannot multiply two vectors together. Okay, but we can take a scalar quantity, multiply it to a vector. For example, if I have a vector p, I can write a 2 times p, but I cannot write a vector q multiplied by vector p. So 2p is okay. What will happen to 2p? 2p is going to be like p, but it is going to be stretched by 2 times, which means that it is going to still bear the same direction, but its magnitude is going to be doubled if it is 2p. If it is half p, then the magnitude is going to be half, which means that it is still going to be in the same direction, but the distance is going to be smaller by half. In fact, this increase in magnitude is very, very easy to be derived if we were to look at P in the column vector form. So let's say, I'm going to make use of this a more general scenario here, okay? So let's say I have this vector A, and vector A, if it can be expressed in the column vector form, so x, y, the x coordinate and the y coordinate of the position vector of A, let's say A is a position vector. So if I were to do a Ka, a scalar multiple of A, that means I'm going to be getting a K times of x, y. To re-express this, like what I wrote there, it will be scalar multiple multiplied by this, scalar multiple multiplied by this. So we will actually be getting a Kx, Ky. Okay, scalar multiple of a column vector is going to be like this. So let's take a look at what is the modulus of this. That means what is the magnitude of this overall vector Ka. The magnitude of this, if I were to apply the formula for magnitude, that means if I were to apply this formula here, it is going to be square root of Kx square plus Ky square, right? By applying the Pythagoras theorem. And this is equal to square root of K square of x square plus y square. And it is going to be square root of K square, it is K, then square root of x square plus y square. And what is square root of x square plus y square? Since A is this, that means modulus of A is going to be square root of x square plus y square. So now we have a K modulus of A, which means that whatever is the magnitude of A, which is this, when I have a K times of A, the new magnitude is just going to be K times of the original magnitude. So if the original magnitude of P is modulus of P, the new magnitude is going to be 2 times the modulus of P. If the original magnitude of P is 5, the new magnitude is going to be 2 times of 5, 10. It is going to be stretched by 2 times. And if A is equal to a scalar multiple of B in general, okay? So if A is equal to KB, this immediately tells us that the two vectors A and B, they are parallel to each other, because the scalar multiple is not going to change the tilt or the slope of the vector B. Okay, it can change the direction. Okay, please take note, there's a difference. So if A is equal to KB, it doesn't change the tilt. So these two vectors, they are going to be parallel to each other. A and B are supposed to be parallel to each other. But if you were to look at the sign of A, if you were to look at the sign of K, if K is bigger than 0, then you know that they are not just parallel, but A and B are in the same direction. But if K is less than 0, they are still going to be parallel, but they are going to be in opposite direction. And if A, B, C are lying on the same straight line, if they are to be lying on the same straight line, there's this new word that maybe you have never come across, then it will be a new word. It is collinear. So if A, B, C are collinear, that means they are lying on the same straight line. I have this as a result. AB is equal to KAC. That means AB is going to be parallel to AC. I'm going to talk about this in a short while also. When we are doing an example later, we will have one case where we're going to apply this collinear, and we'll have one case which is where 3 points are collinear. Okay, so we are going to come back to this again in a short while. So let me skip this first. Let's hold, and we will talk about the next thing first. The next thing I want to talk about is this vector algebra thing, where we are supposed to be adding vectors together, subtracting one vector from another vector. So there are some laws, commutative law, associative law, distributive law. They are very similar to addition and subtraction. So I'm not going to elaborate so much on them. You probably already can execute them pretty well. I want to focus a bit more on the additional law of vectors and the subtraction part. Subtraction part is a little bit it's not exactly a law, but let me talk about it in a short while also. For this addition of vectors, there are 2 laws that can help us to do addition of vectors. They are the triangle law and the parallelogram law. So when 2 vectors are added together, for example, like in this case here, if OA is added to AC, if OA, let's say O is the origin, A is the point here, if C, let's say, is the point here, if OA is added to AC here, then the result is going to be this vector OC. So what I'm trying to say is that according to triangle law, vector OA plus OC, vector OA plus AC. So vector OA plus vector AC, this is going to be vector OC. Okay, they form a triangle. Basically, it is starting from the initial point. I go to A, then after that I go to the terminal point C, then this vector plus this vector will represent this. Similarly, if I can find another root, for example, like the diagram that I've drawn here, if I have another root, for example, this, and then followed by this, let's say this point here is B. If to go from here to here, if by another route, I can also go from O to B, then after that B to C. So even if I were to do a OB, vector OB plus vector BC, I will still be getting this vector OC. This is the triangle law. Okay, we will see a triangle over here. At the same time, there's this other thing called the parallelogram law. Parallelogram law says that if I have two vectors, let's say OA plus another vector OB, and I build a parallelogram where OA and OB are the sides of the parallelogram, then the diagonal of the parallelogram will represent the result of the addition of the two vectors, which means that if I were to apply the parallelogram law, then OA, vector OA plus vector OB here is going to be equal to vector OC. And you think about it, actually they are very, very similar. You know why? Because let's say this is a parallelogram, okay? If this is a parallelogram, vector OB and vector AC, if they were to be this is a parallelogram, okay? So, which means that vector OB, vector AC, they will be in the same direction and they will bear the same magnitude. So they are equal vectors. Same direction, same magnitude. They don't have to be exactly, one on top of another. They don't have to be exactly at the same place. As long as they should bear the same direction and same magnitude, they are equal vectors. Which means that if I were to look at this vector AC is equal to this vector OB. So if I were to just change this, okay, if I were to change this, it will be OA plus OB, which is also the same as AC. This will be equal to OC, and this is the same as this. Okay, so this plus this is going to be OC. This plus this is also going to be equal to OC. Let's take a look at some examples, and we are going to try to make use of some of these theories of vectors that we have talked about. In the worksheet, I have some questions. So let's take a look at some questions here. There are 6 questions. We're going to try them, and we are going to try to make use of some scenarios that are given to strengthen our ideas of vectors. So in this diagram over here, according to what the question says, we have a regular hexagon. So for this regular hexagon, let me just do a quick sketch of it here. It may not be as regular as what I have there, but okay, I'm going to just take it as if it is a regular hexagon. So we have this and yeah. Okay, so for this regular hexagon, this is A, this is B, C, then we have D, E, and F. Okay, so we have this regular hexagon, which some of the vectors, position vector, okay, it starts from the origin. Some of the position vectors are actually given to us. We know that here, this vector here is vector A. We know that from O to here, this vector here is B. And this vector over here, this one is vector C. So with this, we want to find FE. Okay, we want to express vector FE in terms of vector A, B, C. Where is vector FE? It is here. So here we have vector FE. Okay, it starts from F, it terminates at E. Vector FE. So how do we find vector FE? Vector FE is the same as vector BC. Okay, so FE is the same as vector BC. I'm doing part A of this question. Vector FE is equal to vector BC. And the reason why I want to reference it back to vector BC is because we are given the position vector of B, which means that we know that OB is equal to B, and we know the position vector of C. So we know that OC here is equal to C. So because we know this and this, by looking at this, what we can try to do is to make use of the triangle law. We can make use of the triangle law to find vector BC. And how do we find vector BC, which is actually equal to vector FE? To find vector BC, so BC here can be found by going from B to O, then O back to C, correct? So vector BC is going to be BO, vector B to O, then plus O to C. I guess O to C is fine because O to C is just this vector C. But B to O, we don't have B to O. Or at least we don't yet have B to O. We have O to B. But what is O to B and B to O? I mean, how are they related? They are negative vectors, which means that if OB is B, that means BO, vector BO is minus B. So what we can do is to write this as negative of this vector OB. So this is negative of vector OB plus OC. We can already get the result. Okay, we can already get our answer. Our answer is going to be minus B plus C. But I want to generalize this result because this result here is going to be very, very useful. I want to generalize this result by rewriting this as OC minus OB. You know why this is going to be very, very useful? It is extremely useful for those cases where we actually have position vectors that are given to us by the question. Because for example, if I have OB, if I have OC, and if I want to find something that relates to the points that are given, for example B and C, instead of going through this, we can make use of this as the result. Because I can see BC is just, after all this manipulation, is just going to be the position vector of the terminal point, C, minus away the position vector of the initial point, OB. So it is OC minus OB, which is actually highlighted here in the outline. We have talked about addition just now, but we didn't talk about subtraction. So for subtraction wise, okay, we can actually apply this. So it is the same process that I have here. Okay, AB is like AO plus OB, AO plus OB. But I know AO can also be written as minus OA because they are negative of each other. So if I were to rewrite AO as negative of OA, then AB can be found by doing a OB, vector OB, minus vector OA. The end position vector minus away the beginning position vector. With a position vector that represents the terminal point minus away the position vector of the initial point, OB minus OA. Let's memorize this. Okay, it is really going to be very, very practical rule that we can apply for a lot of other questions that we're going to be seeing later, and definitely even more in H2 math. So here, BC is just OC minus OB. So if I can make use of this result, then it is just C minus B. This is going to give us vector FE by making use of subtraction. In fact, it is actually derived from vector triangle addition, by applying the triangle law, vector addition, the triangle law. So now we have gotten FE. Next, we want to find vector AD. This is a regular hexagon, which means that if I were to draw in some lengths here, okay, let me use this. If I were to draw in some lengths here, so for example this, if I were to draw this and this, okay, they are supposed to be cutting at the center, we will have equilateral triangles, small little equilateral triangles, which means that this length and this length and this length, they are actually the same. So I'm going to apply the scalar multiple of vectors, because for B, which we are supposed to be finding vector AD, right? So for B, to find vector AD, with the geometry that we are given, we know it is going to be 2 times of vector FE. So it's going to be 2 times of C minus B. This is our answer for part B. Next, let's try to find vector AF. Okay, let's try to find a vector AF. So to find vector AF, let me clear this away. Okay, so here to here, it is still our vector A. Here to here, it is going to be our vector B, and we have vector C. And we want to find vector AF. So AF is this vector over here. Okay, we want to find vector AF. And to do that, I'm going to reference vector AF to vector CD. They're going to be equal vectors. So to find AF, okay, I'm going to be seeing this as vector CD. So this is part D. So I'm going to see AF as vector CD. So my attempt now is going to be finding vector OD first. Then after that, I will be able to find CD, right? Because if I were to make use of subtraction, the rule that we have discussed, then CD, vector CD can be OD minus OC. So how do we find vector OD? Okay, how do we find vector OD? Hey, we have AD, right? You know, from the previous part, we have found vector AD, and we found vector AD to be 2 of C minus B. And here is where we have D, which means that if I were to take the position vector of the terminal point, OD, minus away the position vector of the initial point, OA, OD minus OA, which is AD, is 2 times of C minus B. And we do know what is vector, the position vector of A. We know what is OA. So OD minus A, this is 2 of C minus B. So now we have vector OD. Vector OD is going to be 2 of C minus B, then plus A. This is vector OD. So OD is this. Now I can find vector CD. Because vector CD, and again by making use of the subtraction rule that we have discussed, it is going to be the position vector of the terminal point minus away the position vector of the initial point. And OD is 2 C minus B plus A, then minus OC. OC is C. This was already given to us by the question. So this is going to be equal to A, then this minus 2B. We are using the distributive law of vectors addition, which is actually just the same as addition. So this, and we have this times this, 2C minus C, it is going to be plus C. So this gives us vector CD, which is vector AF that the question is asking for. Okay, so this is part C. Oh, this is part C, not D. So this is part C. And let's move on to finally part D, okay? So for part D, we are supposed to find vector BF. We are supposed to find vector BF. Let's try. So for part D, to find vector BF, what I'm going to try do is to first find vector. I'm going to make use of vector. Okay, I need the position vector of F. Okay, because if I can find the position vector of F, I know BF here. BF here can be found by going for OF minus OB. The position vector of the terminal point minus away the position vector of the initial point. So BOB I have, it is this vector B here. What I don't have now is OF, and we can find OF because just before this in part C we found vector AF. So by making use of vector AF first, AF from part C, this was found to be A minus 2B plus C. And AF can be expressed as OF minus OA. And this is A minus 2B plus C. So OF is going to be equal to this. If I were to shift it over to the right hand side, it is going to be A plus A. So 2A minus 2B plus C. And now we have OF. We can then find BF. So vector BF, therefore, it is going to be equal to the position vector of the terminal point minus away the position vector of the initial point, OF minus OB. It will be this minus 2B plus C minus away B. So it's going to be this minus this. This will give us a 2A minus 3B plus C. And I have an alternative way to find BF. Let me propose this other strategy to you, okay? It is very, very useful also. It is going to be making use of the triangle law of addition. Because BF from here to here, BF can be found by also going for I'm going to propose an alternative way for us to find OF. Okay, instead of going through this OF from here to here. Okay, OF can also be found by going for a OB plus BA then plus AF. Okay, OF can be found by going from here to here, to here, then to here. OB to BA, then after that plus AF. How is this the triangle law? Let me show you why, okay? So if you think about it, okay, where is our first triangle? If I were to go from O to B, then B to A, then the result is OA, correct? So if I were to go from here to here, this, then after that here to here, this, it gives me OA. Let me erase this first, okay? That means here to here, OA, by triangle law, is going to be OB plus BA, correct? So this vector here is OB plus BA. Then we have our second triangle. Our second triangle will be here, this triangle. So from here to here to here, this is our second triangle. So for this second triangle here, here to here, then to here, for this second triangle here, OF is going to be equal to OA plus AF, correct? It's going to be here to here, here to here. And what is OA? OA is going to be OB plus BA, right? Then plus AF. So we have this. Okay, so it will be this plus this. And now if I were to just remove the bracket, this is actually what I've already quoted. You know, this is actually putting a few different triangles together, adding them together. And it makes it super efficient for us because we can skip the individual triangles and we can just start at maybe one point and we just need to trace another path to our terminal point, regardless of how many triangles we form, regardless of how many paths we are forming. As long as it is possible to trace a continuous path to the terminal point, then this, like what I've just done here, will actually also give us our resultant vector that is like this. And this is very efficient, especially if I already have the individual vectors. OB is vector B plus BA. BA is the end position vector minus away the beginning position vector. The position vector of the terminal point, A, minus away the position vector of the initial point, B. Then plus AF. AF is a vector that I already have from the previous part. So AF is this A minus 2B plus C. And what is my result? My result is A plus A. This I have a 2A. Then B minus 2B I have a minus 2b, then a single c here plus c. I'm getting exactly the same OF. And after I've gotten OF, I will substitute back into here to find BF. It is going to be the same thing. Okay, please remember this. It is actually making use of the triangle law, but extending it such that if we can visually trace a continuous path from the initial point to the terminal point, the addition of all the paths will automatically give me the final resultant vectors. Okay, a very, very useful law that is extended from additional law through the triangle, the addition of vectors through the triangle law. Let me show you another question. Let's take a look at question number 2. So for question number 2 here, we have 2 position vectors that are given to us. We have vector OC and we have vector OD. We are also given that CE is to ED. The distance are of a certain proportion, and the proportion is 4:3. Okay, and we want to find OE, vector OE, in terms of C and D. Let me sketch out the scenario. So we have this. Okay, we have this. And E is, let's say, somewhere here. If C is here and D is here, according to what the question says, the proportion is going to be 4:3. And our aim is to find this vector. This is the origin. Our aim is to find this vector OE. So here. Okay, we are supposed to find this vector. And my plan is this, okay? My plan is to find OE by doing a OC plus CE. Okay, this is my plan. I already know what is OC. This is given to us as vector C. This is given to us as vector D. So what I don't have as of now is CE, the vector CE. But I know CE is parallel to CD. So the first thing that I'm going to do is I'm going to find CD. I'm going to find vector CD first. And vector CD is the position vector of the terminal point, D, minus away the position vector of the initial point, C. So CD is D minus C. And if I can just use this scalar multiple, which I know it is going to stretch the vector or to compress the vector, I can apply a bit of proportioning, right? Because from here, I can see what is vector CE. Because it is just going to be a proportion of 4/7. 4 over 4 plus 3. 4/7 of vector CD. Which means that vector CE is 4/7 of D minus C. And now I'm ready to find vector OE in terms of vector C and vector D. OE is going to be equal to OC plus CE. Okay, I just need to trace, right? From the initial point, I just need to trace a path to here. So I'll go from here to here and here to here. So that gives me a OC plus CE. So OC is C, then plus CE, this is 4/7 of D minus C. So we are talking about C plus 4/7 D minus 4/7 C. So my answer is going to be 3/7 C plus 4/7 D. Question number 1, question number 2 are examples, are problems that we were trying to solve for general vectors. But for H2 math vectors, being able to manipulate and understand column vectors are actually very, very useful. So I'm going to spend the next few minutes, right, looking at at this question number 3, 4, and 5, and 6. So the last few questions here, okay, we're going to be trying them out. We're going to be trying them out based on what we have learned about vectors in general and specifically being applied to column vectors. Okay, column vectors, you can remember, right? Column vectors is like 1, 4, 5, 2. Okay, let's try this question number 3. So for this question number 3, we are told that, okay, there's this parallelogram OABC. O is the origin, and we are given OA is 1, 4. Okay, and because it starts from the origin, OA is a position vector. OA is a position vector. OA, which is this 1, 4, is a position vector. This tells me that the coordinate of the point A is at 1, 4. And please, let's be reminded, okay, we are talking about position vector. That is why the coordinates of A is 1, 4. If we are given just 1, 4 as a column vector, it may not imply that the terminal point or the initial point has anything to do with this 1, 4. Similarly, we are given OC. We are given OC as 5, 2. So OC, this is 5, 2. This tells us that the coordinates of C is 5, 2 because we are looking at a position vector. On the diagram, we want to clearly label A, B, C. I'm definitely going to do A and C first. So let me sketch out the diagram. Let's say this is the y-axis. Let me draw a little bit longer. So this is the x-axis. This is the y-axis. I'm going to do some markings here. So 1, 2, 3, 4, 5, 6. And let's say here is also 1, 2, 3, 4, 5, let's say 6. So 1, 4, 1, 4 tells me that if this is the origin 1, 1, 2, 3, 4, point A is going to be somewhere here. Point A. So this is at the point 1, 4. Okay, 1, 4. And point C is 5, 2. So 1, 2, 3, 4, 5, 5, 1, 2. So maybe somewhere here, this is point C. Its coordinate is 5, 2. So here is 5, here is, let's say, 2. And we're talking about a parallelogram, OABC. So for OABC, we're expecting something that is like this. This is OAC, which we have just drawn, so B should be somewhere here. And since this question tells us that it is a parallelogram, so I know this length and this length must be the same, these two lengths must be the same, and they must be having the same slope. Okay, they must be parallel to each other. Okay, the opposite sides must be parallel to each other. Which means that from here to here, it goes 5, 2. That means from here to point B, you should also go 5, then 2, correct? The x-coordinate is 1. If I were to go 5, I will reach 6. The y-coordinate is 4. If I were to go up by 2, I'm also going to reach 6. So at the point 6, I will have this point here. Let's say this point here. This is going to represent for us point B. And like what we have just calculated using the idea of parallelogram, we know the coordinates is 6, 6. Let me repeat again. From here, from O to C, it is this part here. It is going to be the same magnitude and it's going to be the same slope. So if from here to here goes 5 and 2, that means from A to B, you should also go 5 and 2. And now the parallelogram should look something that is like this here. And this AB should be the same as this OC. And this OA should be the same as this CB. So we have a parallelogram. In fact, I've drawn a nicer diagram here for us. It is this here, okay? So if you have drawn it, then you should have something that is like this. So now we have this parallelogram and we have already labeled B. We want to express the column vector, we want to express in column vector OB, CA. OB has a coordinates, point B has a coordinate of 6, 6. And since the question wants vector OB, it is a position vector. So it is going to be related to the coordinates of the terminal point here, which means that OB is going to be equal to 6. 6. That is, if I were to rely on coordinate geometry. 5, 2, 5, 2, we can even count from the squares here, okay? It is going to be at 6, 6. So we know this vector here, OB, this vector here is 6, 6. But haven't we discussed something that we can actually apply to a scenario that is like this? We can apply addition law. We can apply the parallelogram law. Because we do have a parallelogram here. The question says that OABC is a parallelogram. So in order for us to get OB, if we were to not just count squares on the Cartesian axis, what if we were to apply vectors? Let's try. Okay, we have already gotten an answer. Okay, we are just trying to explore what can we do if I were to apply vectors addition. So I know OB can also be OA. If I were to apply the parallelogram law, OA plus OC. Okay, OB, and this is a parallelogram, so it can be OA plus OC, parallelogram law of addition for vectors. So what is OA? OA was given to us as 1, 4, and OC was given to us as 5, 2. So this plus this, it will be this plus this, it is 6. This plus this, which is also 6, is synchronized. Okay, that is why position vector and coordinates are very, very closely related. And that is also why Cartesian axis is a very useful way for us to find representations for vectors. But how about the triangle law? Do you think the triangle law will also work for finding OB? If I were to apply the triangle law, to find OB, we can actually add OA, AB, right? This forms for us a triangle. So if I can do a OA plus AB. And we know what is this vector OA. Vector OA was given to us as 1, 4. How about AB? Vector AB shares the same direction as OC and the same magnitude as OC. So AB is the same as vector OC. And if you think about it, vector OC is 5, 2, which means that if you were to see geometrically, OA is also 5, 2, which was how we plotted B just now, right? And furthermore, since we have just discussed they are the same vector, they are equal vectors, so AB will also be this 5, 2, which will then give us 6, 6. It is exactly the same thing. That is why using a Cartesian axis to represent vector is actually very, very efficient, because it shows us in a lot of different ways, especially when it is familiar to us for whatever that we have done using the Cartesian axis since our secondary school. It gives us a better grasp of vectors. And that is why column vectors is actually very much used in H2 math also. Let's make sure that we get this. So we have vector OB. Let's take a look at how we can find vector CA. Vector CA. So for vector CA, how about making use of the subtraction rule that we talked about just now? So for vector CA, it is going to be the position vector of the terminal point minus away the position vector of the initial point. So it is going to be OA, which is 1, 4, minus away OC, which is 5, 2. And the result is minus 4, 2. And if you were to just count squares, okay, you're going to get exactly the same thing as this. Minus 4, 2. How will that be? Because if you were to count squares, CA, it is going from here to here. Horizontal wise, it's going to go left by 1, 2, 3, 4, minus 4. Vertical wise, it is going to go up by 2 units. So from here, 1, 2 to get to A. That is why it is going to be a positive 2. Again, these two synchronize. Column vector, Cartesian axis. Let's try some more. Let's take a look at question number 4. In question number 4a, we are given that P is equal to 2, 3. We are given that vector Q here is minus 3, 5. Okay, and the question didn't tell us that they are position vectors, so we are just going to assume that they are vectors in general. They can be starting from the origin, they can be somewhere else, we are not very sure. We are supposed to find modulus of P plus Q. We are supposed to find the magnitude of the vector P plus Q. So the first thing that I'm going to do is to find P plus Q. And this is going to be 2, 3 plus minus 3, 5. So it will be 2 minus 3, this is minus 1. 3 plus 5, this is 8. So we have this vector, and we are supposed to find the modulus of P plus Q. And do you remember how to find the modulus or the magnitude of a vector? We have it here. In our outline, we have just talked about it. The magnitude of a vector is going to be square root of x squared plus y squared. So in this case, it is going to be square root of minus 1 square plus 8 square. This is going to be square root of 1 plus 64. This is square root of 65. Modulus of P plus Q. Let's take a look at another one so that we can get even more used to working on column vectors. The position vector of A and B. Okay, this time they are defining for us position vectors. Like what we have mentioned just now, if we are given vectors, we will just assume that they are vectors in general. We will assume that they are free vectors until when we are told that the vectors that we are working on are position vectors. And now we are in part B. We are working with position vectors of A, OA, which is this A here. This is equal to 3, 4. The position vector of B, which is given to us as B here, this is minus 2, 5. And we are given position vector OC as 2A plus 3B. And we are supposed to find the coordinates of C. So we know position vectors are very closely related to coordinates of the terminal point. And so that is why I'm going to try to work out this vector OC first. It is going to be 2 times of A, which is 3, 4, plus 3 times of B, which is minus 2, 5. So we have a 2 times 3, 6, 8, plus this is going to be minus 6 and 15. So this is going to be 0. This is equal to 23. So the column vector of this position vector OC is 0, 23. Therefore, we know that C is 0, 23. Let's try OD. It is going to be the same thing. OD is equal to 2A minus 2B. Okay, 2A minus 2B. So it's going to be 2 times of A, which is 3, 4, minus 2 times of B, which is minus 2, 5. And this is equal to 6, 8. Then minus 4, 10. So we have a 6 minus 4, it is going to be equal to 10. 8 minus 10, this is minus 2. So the column vector of D, OD is 10 minus 2. In case you're wondering about this negative, we can also definitely bring this negative inside as I multiply the scalar multiple in, which means that another way for me to do the next step, instead of leaving the negative outside, we can definitely do this times this, it is 6, this times this, which is 8. Then plus, I'm going to multiply the entire negative 2 in, so plus positive 4, then this is minus 10. So 6 plus 4, 10, 8 plus minus 10 is minus 2. And since this is a position vector, this tells us that the coordinates of D will be 10 and minus 2. Okay, let's take a look at question number 5. Let's check out this question over here. So for question number 5, we are given vectors, and this is general vectors. We don't know whether they are position vectors. We are given that OP is 5 minus 3. We are given that Q is 4, 7. And we are given that R is this 8M. Okay, we are given this. I want to express two vectors in column vector form. A part 1, A part 2. So for A part 1, we are looking at 3p plus q. 3p plus q will be 3 times of 3 minus 5 plus q for 7. So this will be 9 plus 4. This is going to be 13. And it will be minus 15 plus 7. It is going to be minus 8. So 3p plus q. And in part 2, we are looking at p minus 2r. So it is going to be p, this is equal to 3 minus 5 minus 2r. R is 8m. So in column vector form, it will be 3 minus 16. 3 minus 16 is going to be minus 13. And minus 5 minus 2m. So we have p minus 2r. Part B. Part B, we are told that these two vectors, 3p plus q, p minus 2r, they are parallel. And by making use of this, we want to find the value of m. And since they are parallel, we are going to make use of what we have discussed too. It is going to be this. Okay, when two vectors are parallel to each other, then they are scalar multiple of each other. So what I'm going to do is, I'm going to let this vector, 3p plus q, be equal to a scalar multiple of this, which is p minus 2r. So 3p plus q, we have evaluated it to be 13 minus 8. This is equal to k times of minus 13 minus 5 minus 2m. So 13 minus 8 is going to be equal to minus 13k and k times of minus 5 minus 2m. If I were to look at the first row, comparing the left and the right, I know that 13 is equal to minus 13k. This will actually help me to solve for k. K is minus 1. Actually, what does this tell us? This tells us that this vector is a negative scalar multiple of this vector. According to what we have just discussed here, if one vector is k times of another vector, if this scalar multiple is less than 0, which is what we are seeing here, k is negative, then they are in the opposite direction. Anyway, what we are supposed to find is m, so this is just our discussion. So m, in order for me to find that, I'm going to make use of the second row, which is minus 8. This is equal to k, which is minus 1, minus 5 minus 2m. So minus 8 is going to be equal to 5 plus 2m. M will be equal to minus 8 minus 5 divided by 2. So now we have solved for m. It is minus 13 over 2. Okay, let's look at one last question. Question number 6. Here. Okay, let's try out this question. We're now given a diagram, and this diagram is on a xy axis, on the Cartesian plane. We are given point E with coordinates as 1, 1. Okay, I'm not sure whether we are going to be using it yet. Actually, we will be, but if the coordinates of E is 1, 1, that means the position vector of E, OE, will be 1, 1. CE is given to us as minus 4, 2. AED, BCD, they are straight lines. Part A1 require us to find the modulus of CE. This is extremely easy. It is just for us to find the magnitude of CE, which means that we are supposed to be finding the magnitude of minus 4 minus 2. And this is going to be square root of minus 4 square plus minus 2 square. And this is going to be equal to square root of 16 plus 4. This is going to be square root of 20, and it will be 4 times 5, so 2 square root of 5. Then part 2. Part 2, we are supposed to find the coordinates of C. And to find the coordinates of C, we know that CE here is given to us as minus 4 minus 2. CE is minus 4 minus 2, which means that if I were to use the position vector of the terminal point, which is OE, minus away the position vector of the initial point, which is OC. This will also be minus 4, minus 2. And this should help us to find OC because we do know what is OE, correct? With the coordinates of E that is given to us, OE will be 1, 1 minus OC. This is minus 4, minus 2, which means that OC is going to be 1, 1 minus 4, minus 2. So this will give us a 5 and a 3. OC is going to be 5, 3, which means that the coordinates of C, which is what the question is asking for, is 5, 3. So part 2. Next, B. In B, we are given the coordinates of point A as minus 2, 3. And AB is equal to 3 over 2 EC. We are supposed to find the coordinates of B. Let's write down this. We know AB here is equal to 3 over 2 EC. AB, we can actually re-express it as the position vector of the terminal point minus away the position vector of the initial point. And this is equal to 3 over 2 EC. Do we have EC? We do not have EC. But if you were to look at the question, we do have CE. So EC, CE, they are negative vector, which means that I can rewrite this as minus CE. So we have this, which means that we are going to be working on OB, which is given to us as, we have already found OB. OB is, we are supposed to find OB. Okay, so OB, I'm going to leave it as it is. Minus OA. OA is minus 2, 3. This is equal to 3 over 2 minus CE. CE was given to us as minus 4, minus 2. So negative of this is going to be 4, 2. Negative of CE. Okay, negative of minus 4, minus 2 is 4, 2. So OB, vector OB, is going to be this. Let me just multiply this in. So 3 over 2 times 4, it is going to be equal to 6. This times this is going to be 3. So 3 plus minus 2, 3. And this is equal to 6 minus this. This is 4. This is going to be equal to 6. And what is the coordinates of B since we have now found the position vector of B? Therefore, the coordinates of B will be 4, 6. And the last part, part C. So in part C, we are given the coordinates of D. We want to find the vector AD in column vector form in terms of H. So for part 1, AD here. AD here is going to be the position vector of the terminal point minus away the position vector of the initial point. The coordinates of D is given to us as H minus 3. So the position vector of D will be H minus 3 minus away OA. The coordinates of A is given to us in the diagram. It is minus 2, 3. So here is minus 2, 3. Which means that AD is going to be equal to H plus 2 minus 3, this is minus 6. AD in the column vector form expressed in terms of H. And the one last part, part 2. Part 2, given that AED is a straight line, I want to find H. AED is a straight line. AED is a straight line, which means that point A, point E, point D, they lie on the same straight line. This brings us back to what we have skipped just now, the idea of collinearity. When 3 points are collinear, for example, this A, B, C, when A, B, C are collinear, when A, B, C lies on the same straight line, we can say that AB is equal to KA, C. In general, what does this mean? This means that these two vectors, they are parallel to each other, which means that vector AB is going to be parallel to another vector, which is AC. But what is so special about these two vectors that are parallel? These two vectors share the same point, which means that when the two vectors are parallel and they share the same point, point A, that means this point is not away from it, but it is actually at exactly the same place, which means that AC has to be here. C is going to be here. That is why if the two vectors are parallel to each other and there are common points on the two vectors, for example, in this case, A, then we can say that A, B, C, they have to be lying on the same straight line, which means that it is not necessary if A, B, C are on the same straight line that it is AB is equal to KAC. There are other variations. Okay, so although in the outline here, I wrote it as AB is equal to KAC, but if A, B, C are lying on the same straight line, we can also say AB is equal to KBC because they are parallel and they share a common point, B. Or any other variations, all will be fine. This is the idea about collinearity. When 3 points are lying on the same straight line, then you can just pick any 2 points. And for these 2 points, if you were to come up with a vectors that join the 2 points, you should derive at either this or some other variation where the 2 vectors are parallel to each other and they should share the same point. I'm going to apply this to this last part of the question, AED. Since AED lies on the same straight line, and we have AD here, that means AE must be parallel to AE must be parallel to AD. Okay, so let's try to find AE first. AE will be the position vector of the terminal point minus away the position vector of the initial point. OE is 1, 1. OA is minus 2, 3. So this is 1 minus minus 2, 1 plus 2, this is 3, and this is minus 2. Okay, this is AE. And since AED are collinear, I can see that from the diagram, it is also mentioned to us as a descriptive in the question. That means I can let, for example, AE, I'll let vector AE be equal to K vector AD. So AE, this is 3 minus 2, is equal to K. AD, this is H plus 2 minus 6. And this will mean that minus 3, 2 is equal to K times of this minus 6K is equal to this. And now using the second row, we have a minus 2 is equal to minus 6K. This tells me that K is equal to 1 over 3. It is positive. Okay, unlike the previous question, we got K to be a negative number. Here we got K to be a positive number, which means that AE, AD, they are in the same direction. In fact, I can see that in the diagram, right? Can you see from the diagram, AE, AD, they are all pointing in the same direction. So we have found K. I'm going to now find H. So from here, using the first row, 3 is equal to 1 over 3, H plus 2. So multiply over, I have a 9, 9 is equal to H plus 2. This tells me that H is equal to 9 minus 2, H is equal to 7. This is the last question that we're going to be working on. And what I hope that we can achieve is for us to get familiarized with how vectors work, what is a vector, and how it works specifically for a two-dimensional space. This was what that had been taught in your secondary school. And if you can get familiarized with this, then it is time to move on to the H2 Math vectors, where we're going to be dealing with vectors in 3D.